All right, in this video I'm going to be talking about the absorption or emission spectrum of a gas and what that told us about the atom. So in the last video on the gold foil experiment, we came up with a new model for the atom. We knew that it had to have this incredibly dense positive nuclear core, and then we had these electrons that were sort of floating outside the core. And there's still one significant issue with this atom. It was unclear why these electrons didn't just fall into that positive nuclear core. Now, somebody came up with sort of the obvious analogy to our solar system. If we think of the positive dense nuclear core as the sun, and then we imagine these electrons orbiting the sun, then if they orbit at a constant radius with some specific velocity, maybe they could be in a stable orbit around the sun, just like, say, the Earth is. But the problem with this is that as this electron moves around this circle, according to our understanding at the time, that should have made some electromagnetic radiation, something that we consider something like light. And what that would have done is caused this electron to lose energy as it spat out energy or released energy. And what that would have done is caused this electron to spiral into the nucleus until it did eventually hit and blow up. So why doesn't it spiral in and fall in? Well, we're not actually going to address this issue really clearly in this video. Instead, what we're going to do is look at the next experiment that gives us a little bit better of a picture, and maybe a video much later will try and address why it doesn't spiral in. But right now, we're just going to get our next model or our next discovery that came along to improve our understanding of the situation. So what they were doing when they did this experiment is they were taking a gas. So they would have a tube, and this tube was full of gas, let's say something like helium. And they would put two batteries at either end. So they'd put a positive end of a battery and a negative end of a battery. So this would be attached to some giant battery. And the thing with gases is that they're not typically good conductors of electricity. And so if you have a battery out in the air, it's not going to have enough electricity to force the electrons to move through that empty space. However, if you have a giant battery like this, you can push the gas hard enough that it will conduct electricity. And what happens if we think about it is that maybe in the gas there are helium atoms who have their two electrons. What happens is that helium electron that will get so much energy it'll jump away even though it doesn't want to and leave that helium atom. And that'll be passing by other helium atoms. And maybe as it's passing by helium atoms, one of these other helium atoms will have lost its electron, and as a result he won't be there, and what will be there instead is a hole. When this electron's going by conducting electricity, because there's just so much energy forcing it to do it, there's some chance that that electron will jump back into that helium atom who has a hole because he gave up his electron earlier. This is a gas discharge tube, and this is one of the ways that we produce light in things like neon lights that we use to show maybe the open sign of a shop that's open at night. So when this electron jumps back into that helium atom, when he moved up here, he had to absorb energy. So when he jumps back down, he gets to release energy. And the way that he releases that energy is as electromagnetic radiation or light. So we put this gigantic battery, and it forces the electrons to leave their helium atoms and conduct electricity even though they don't like to do that in general. They move along the system, and eventually they see somebody else who's kicked out or who's lost their electron, and they jump back in, releasing light. Some of them will make it all the way from the negative to the positive plate and allow this whole system to conduct, but lots of them will leave and then jump back in. And most importantly, when they jump back in, they spit out light. So this tube starts to glow. Then what we do is we take a special machine called the diffraction grating. And for the purposes of this argument, all we have to really understand about a diffraction grating is that it's some sort of special device that separates the different colors of light. So we can get it so that red light will go this way and blue light will go that way and green light will go somewhere in between those two things. And we can think of this kind of like a prism where we're going to then see the rainbow of the colors. But what's important about that is that we can find out what colors of gas are being produced when we force this gas to conduct electricity. All of that's pretty complicated, and to understand it more, you can look up things, videos that I've done on stuff like the photoelectric effect and stuff like that. But what's important about all of this is that when we did this, we found, and then we made a graph of color versus amount of light. What we found is that some colors produced a lot of light, while lots of other colors didn't produce very much or any light at all. So we would get a lot of light here, or here, and then in this whole region, we would get no light. So to go back to our analogy up here, maybe we get blue light and maybe we get red light, but we get no green light. We get no orange light. We get no purple light. So there's only specific colors of light that are being produced. What Bohr interpreted this as is important to this specific section of this process. So here's our helium atom, and here's the hole, or here's where he's missing an electron, and here's the electron that's zooming by. What Bohr assumed then is that the color of light must correspond to a different amount of energy change that must be associated with a different amount of energy change when this electron drops back in to the helium atom. So what we can imagine then is that maybe there are 3 different holes that the electron could jump into. If it jumps all the way down, that would be a large energy change, or maybe a spike over here, that might be like 1. If it jumps instead just a little bit of the way down, that may be like that peak there, 3. And if it jumped halfway down, we'll call that 2, and that might be like that peak right there. But what's interesting about it is that there appear to be these forbidden regions where the electrons don't jump to. And we can tell that these exist because we have these weird bands of forbidden colors. This led to Bohr coming up with a new model of the atom, something that we're not going to fully explain right now, but that looked something like this. He kept the small positive nuclear core. In fact, any model of the atom that we currently have still has that nucleus. But what he added were these rings of what we think of as allowable spaces for electrons. So now we know that there are 2 electrons that can fit into the first allowable region, and then as our atoms get bigger, we get these bigger allowable regions that can hold more electrons. So we know that an electron can be in what we call the n equals 1 shell, or it can be in what we call the n equals 2 shell, but we know for some weird reason electrons do not seem to be able to be in a n equals 1.5 shell. Now, why all this is happening is all really well understood from a quantum mechanics perspective, but for now, this is sort of for our grade 11 chemistry course where we're going to get off of this bus, we're going to accept this model, and we're going to use this model to understand how it relates to chemical reactivity. There is more knowledge here. Why are they in these shells? This is the big question, right? Why are some shells or orbits okay while others are not? And that's a big question for the future, and at some other point we will discuss that. But right now we're going to accept our evidence of the existence of the shells, and then we're going to use that as our model for the atom and see how that relates to our periodic table and a number of other things like that.